6 to 10 on Fridays, and then Saturdays.
Well, we're in section 3.2. Before we go on in 3.2, do you have any homework questions you'd like to go over?
Okay, I have
Yes.
them,
One of the assignments, I think it was seventh one. It was one that was a collection of expressions and you could understand some of them.
Do you know what section it was? 3.1 or 3.2? 3.2? And you don't know which one though, huh?
It was actually called one, but I haven't done it was. Well, there's multiple, but the second one was just specifically there was an equation in the second one, and I didn't know.
The set of solutions to this equation? X squared minus 36 is 0. So this equation, if you remember from algebra, this equation has two answers, the number 6 and the number -6. So there's two answers, so this would be finite. If you didn't remember that from algebra, though, this would be kind of hard, so finite.
And then there was the chapter 9, the Mindscape 9.
Yeah, that's the same one, I think. Yeah, this one.
So I believe we all have a different problem for Mindscape 9.
As long as they got the basic.
I can't use the browser here, can I? Oh, yeah, that's working okay. So mine is multiples of 4. So I'm making a one-to-one correspondence between the natural numbers and multiples of 4. So if you write those out on a list, you would write out the natural numbers, and then the multiples of 4, or whatever yours is, and you would be able to use a pen to show the correspondence: 1 with 4, 2 with 8, 3 with 12, 4 with 16. But you can't use that little double arrow in the box on the Adobe Flash entry here. Instead, what I'll do is say 4n. So 4 times n. So n is the number in the first column, like 1 or 2 or 3, and then it goes with 4 times that. That's in the second column. So here I have 1 goes with 4, 2 goes with 8, 3 goes with 12, and so on. And I say that with 4n. Do you have to put a little time symbol in, like that? Did anybody try that?
I didn't try that yet.
Okay, so mine is 4n. You might have 8n or 3n or something like that. I don't think this is going to work because it doesn't, well, I guess it did work. Okay. Any other questions? Okay, then we will continue on in 3.2. The opening question in 3.2 we had answered. How much bigger is the set of rational numbers than the set of natural numbers? In fact, that was what we entered in for the Dropbox for that section. What was the answer? Does anyone remember? How much bigger is the set of rational numbers than the set of natural numbers? So the natural numbers are 1, 2, 3, 4, etc., and the natural, they're the same. Yeah, the same size. They're the same size.
They have the same card.
They have the same cardinality. Yeah, and that's kind of weird because you can see the natural numbers inside the rational numbers. So the rational numbers were the fractions. So you could write that in set notation, the little fractions a over b, and then this vertical bar is read such that a and b are integers and b is not 0. So those are the rational numbers, and then the natural numbers were those counting numbers that feel natural to count with. And the rational numbers have density. Between every two rational numbers, there's another rational number. That's not true for the integers, for the natural numbers. Between every two natural numbers, like 2 and 3, there's not another natural number. So these rational numbers are dense, and yet we were able to make one-to-one correspondence between the rational numbers and the natural numbers. It did take some work, though, right? It wasn't a real evident one-to-one pairing. You had to work it out. So a life lesson in that section is just because a specific attempt failed does not mean that the task at hand is impossible. So I'd ask you to make a one-to-one pairing, if possible, between the integers and the natural numbers. So the integers are the negative natural numbers, 0, and then the natural numbers. So here again you have a set that has the natural numbers inside of it, and yet we were able to come up with a one-to-one pairing. It did take some work, though. So these all have the same cardinality as the natural numbers. And as I was saying, the life lesson in this section, just because a specific attempt failed does not mean that the task at hand is impossible. So we're doing a math appreciation class so we can appreciate some of the ideas of math. And you might not use sizes of infinity specifically in your everyday life, but these ideas of how we look at things and how we study things out, hopefully you will use. As a matter of fact, looking at this life lesson, does anybody know what 10WD40 is? No, wait, not 10W. Just WD-40. Who knows what WD-40 is? Yes. What is it?
Oil.
Yeah, it's an oil. And yes.
Lubricant.
Pardon?
Like a lubricant.
A lubricant. Yeah, and you spray it on your nuts and bolts when they're stuck together, and your wrench won't get them apart because they're so rusted together. Well, who knows what the 40 stands for in WD-40? Yes.
Isn't the 40th formula thing to it?
Yes, it was the 40th formula that it took before they got the one that worked. So this idea of trying over and over till you get it right, that's a good idea in many fields. Well, we're going to explore more of the interesting aspects that can occur from working with infinity. In particular, the size of infinity, that's the same size as the natural numbers, when we look at an experiment. So we're still in 3.2, and we're looking at this experiment. So the experiment has a time limit. It will take 1 minute. The experiment starts with a big empty barrel, but the barrel is soon getting filled up with ping pong balls. And these ping pong balls are labeled 1, 2, 3, 4, 5, 6. In fact, they're labeled with the natural numbers. So that's how many ping pong balls there are. There is a one-to-one correspondence between the natural numbers and the ping pong balls, and hence the ping pong balls are labeled. And here's how this experiment works. We have a task. The first task takes half the time we have, 1/2 of a minute. And in that first task, balls are added to the barrel. In fact, the balls numbered 1 through 10 are added to the barrel. And then, during that half minute, a ball is removed, the ball labeled number 1. So that's the first task. Then we go on to the second task. So each task has half of the time remaining left. So there's half a minute left, and half of that is a fourth. So there's a fourth of a minute, And we're going to, during that fourth of a minute in the second task, we'll add balls labeled 11 through 20. And then we'll reach in and take out ball number 2. So every task, we pour 10 balls in, take a ball out. So task 3 now, we have half of the time left. So we've used a half a minute and a fourth of a minute. Now there's an eighth of a minute left. 1/8. Well, there's a fourth of a minute left, but we're using half that time. So there's an eighth of a minute that we're using for this task. We put in balls 21 through 30, and then we reach in, take out ball number 3, and throw it away. So now we're going really fast here because we keep having the time that we have cut in half. So each of your tasks, you have to go faster and faster. So we're granting you the ability to move infinitely fast here. So now you have 1/16 of a minute for the fourth task. In go balls 31 to 40. They're just rolling down that ramp. And you reach in, pick out ball number 4, and throw it out. So you're going faster and faster and faster. And you just keep doing this so that on the nth task, your time that you have is 1 divided by 2 to the n minutes. So you notice when you were on task 1, then you had 1 over 2 minutes. In task 2, you had 1 over 4, which is 2 times 2. In task 3, you had 1 over 8, which is 2 times 2 times 2. And in task 4, you have 2 times 2 times 2 times 2. You have 4 2's multiplying together. So in the nth task, your time is really tiny. It's just 1 over 2 to the n. And you're taking out the balls that would end in n0 here. So I'm not going to try and write that out. And you remove the nth ball. So we put ... because this goes on infinitely. Because how many time segments can you break up 1 minute into? If I keep breaking them in half, how many times can I do that? As many as you want. You can do that infinitely many, because you just get tinier and tinier and tinier and tinier. So I'd like you to work in groups and answer how many balls. So the minute ends. 1 minute ends. And I'd like you to answer how many balls are in the barrel after 1 minute. Okay? So I bring these ideas home and I talk to my husband about them. And this is where we had our first argument in 32 years. No, I'm just kidding. See if you have an argument in your group, okay? Yeah, we've been married 32 years now. Yep. Okay, so talk in your groups here. I was married as a small child.
Because 1 through 10, 2, 41, 7, 9, I'm kind of confused on how to use this.
So you two could work together and you could eat together. Or you could overhear each other. All done in 1 minute. Do you have any ideas? Oh yeah, you did 2 minutes. Yes, because time keeps going. But if you mean that you never finish all your tasks, then yeah. Well, okay, that's a good point. So the idea is, how could you finish all your tasks? Because there's infinite tasks. But we will grant you powers to be able to do infinite tasks in 1 minute. Okay. Okay. And in fact, there is a mathematical formula for adding up these little parts of the minute. It is true that if you take a half plus a fourth plus an eighth plus a 16th plus and so on, that does actually add up to 1. So that is mathematically correct. So you do, if you're taking out your calculator and trying to do that, you're not going to see it because your calculator, you're doing finite, right? You're not physically able to do infinite things in your calculator. So this is an idea that you're wrestling with more than an actual physical do it. Okay, so if you can do infinite tasks and they're time slotted in this way so that it all comes to an end in a minute, how many balls would there be in the barrel after 1 minute? So let's see if anybody figured it out. Yeah.
So are you supposed to know?
Okay. So you're saying if you do it finitely, then you can say, okay, there's 9 balls here, and 9 balls here, and 9 balls here. Are you doing it?
Well, because, I mean, it has to be balls, but you can, I guess, I don't know. I'm just confused.
That's good. It's a confusing question. If anybody has the answer, raise your hand. Okay, let me give you another hint, okay? Well, let's pick it out. Answer in your groups. Are these balls with these labels in the barrel? So answer those in your groups, okay?
We're just moving.
Every time, like 10 minutes in, you're still moving one.
I don't think by the end of the minute it's good.
Yeah. By the end of the minute, there'll be 9 in there.
Technically, this one should be in there. Because it said by, it said 1/4 of a minute, 2 should be gone.
Any of the ones that somebody
Already, it's really there.
So 20,
very tiny, very tiny.
20 should be in the barrel.
Well, right, but it goes on its back.
Well, I guess I wonder.
So eventually it takes it down. I'm thinking there's nothing. I'm thinking there's nothing in the barrel.
There's air in the barrel.
There's nothing in the
There's
barrel.
air.
It is an airtight container.
That
With
an opening. When the balls go in.
Yeah, so there's still more time left.
After that, each task, you know, etc.
Yeah, you're not at a full minute yet. So there's
Because
Yeah.
two's not in there.
and we can keep doing that.
Eventually.
Do that forever, even past the time your calculator's gonna think it's 1 because your calculator ran out of decimal places.
Right.
Yeah. Yep.
So by the 20th task.
Yep, that's what's going on.
So there's 4.
So eventually your calculator's gonna think it's 1 because it's gonna run into round off error, but it's still not 1.
Right.
Yeah, okay.
So now I'm at 9 ball.
That's what I thought. Is the 20th ball in there? I don't know if that's what the 20th.
No, one of those balls is 22392. Are those like the 426 balls or anything?
Yeah, is that one in the barrel? Oh, it's still in the barrel? So we didn't get it gotten out at the, well, what did you say? Do you think that's the 425th ball in the barrel? Well, let's see. Okay, the infinite task.
Sometimes it's this one. Sometimes it's this one. What did you
Well, I see you're working it out, and that is excellent. So is ball number 2 in the barrel? No, it's gone. Here. Is ball 20 in the barrel?
Yes.
Oh, it would have got gone on the 20th task, right?
Yeah.
20th task. So there's a 20th task here. So that's where ball 20 got taken out. How about ball 392? It got taken out too in the 397nd task. Ball 425 got taken out when?
On the
425th task. There's none in the barrel. Yeah, some of you figured it out. There's none in the barrel. It's kind of a trick question though, because it kind of feels like, well, there should be like every split instant of time, there's 9 balls in and 1 comes out. That's actually a red herring. Does anyone know what a red herring? What is a red herring?
It's something in a story that's there to distract you.
It's something in a story there to distract you. And the red herring here is that the balls are added 10 at a time. It is mean. Okay, if you think of this again, where start with all the balls in the barrel. If you start with all the balls in the barrel, then it's a little easier to picture, right? Because then you can just say, okay, you got task 1, out comes ball 1. Task 2, out comes ball 2. Task 3, out comes ball 3, and so on. And that, if you can do infinite steps in a minute, then each ball is coming out in its task, in its allotted time slot. Does anybody have any questions? Okay. Well, that's one of the strange things that we could run into with ideas about infinity, that sets that at first glance seem larger than other sets are the same size as long as they can be put into a one-to-one correspondence, right? So remember, that's why we took 2 sets like the sets of your fingers and said if the sets can be put into a one-to-one correspondence, they are the same size. And that's why we have to go back to that definition and rely on, is there some way we can make a one-to-one correspondence? Well, we're going to continue our search for larger sets in section 3.3, because at this point it looks like all of the infinite sets we have are size n. In 3.3, the question starts off, is there a set larger than n? So to do that, we're going to take a look at dodgeball. I don't know if you remembered on the first day of class when we did dodgeball, but I had said we would come back to this to help us with infinity, so that's what we're doing in 3.3. Does anyone remember how to win?
Yeah.
Let's see.
You just
So
do
you're,
the second part.
Yeah, you gotta be the second player. Player 1 wants a match, and player 2 is dodging. So player 2 wins if there isn't a match. Okay, so does anyone remember well enough to be player 2 if I'm player 1?
Yeah.
Okay, I heard you first, so you can be player 2 then. Okay, so I'll be player 1. I'll fill out this ever popular text, okay, and what would you be then, player 2?
Or circle.
What did you say?
Circle.
Circle. Okay. Okay, then now I get to go. Okay, player 2,
Circle.
circle. Okay, player 2,
X.
X. Okay,
X.
X. Okay,
X.
X.
O.
Oh, okay. Well, you did win. There is no match. You did good. You're remembering. Does anybody remember enough to explain what player 2 was doing? What was player 2 doing?
She was doing the opposite of what you were doing.
She did the opposite of what I was doing on which entry?
Well, for the first one, the second one, the second one.
Good.
So on and so forth.
So first one, missed that one.
Basically, the diagonal.
Yeah, so she focused on the diagonal. So if the third entry didn't match the third row's third entry, then I wouldn't match the third row. If the fourth entry didn't match the fourth row's fourth entry, then it's not going to match the fourth row. If the fifth entry does not match the fifth entries on the fifth row, then it won't match. And on the sixth row, if the sixth entry doesn't match, it's not going to match. So you just had to focus on one box then instead of the whole row. You just had to differ from one box. Well, I want to make sure everybody knows how to be player 2 and win. So online students, you should download one of these and make sure you understand player 2's winning strategy. I'll hand these out. So everybody get a chance to be player 2, okay? And if you're playing with someone who doesn't understand player 2's winning strategy, then help them out, please.
I made a mistake. That's one beforehand.
And then have player 1. Exactly.
So everybody get a chance to be player 2 and making sure you know how to win, okay?
Thank you. Because this is so weird, because I used to do that.
Thank you.
So it sounded like you didn't remember. So what would you? I wasn't here. I was not involved. Oh, like okay, you be player 2 first.
I leave.
Yeah, you be player 2 first.
Keep the character in short house.
Oh yeah, sure.
Or should we try to come again?
Okay, so you do. Oh, okay, then you can be player 1 first. He'll explain what he's doing while you do it. Okay. And then you get a chance to be player 2.
I guess we have. All right. Player 1.
Same count.
Find a way to make a pattern or a different one and not pattern ever line. But there's never the same pattern. Now, you can just try. I'll pick the guy. There's a pattern. They let usually the opposite the first one. Yeah, of course. You do the opposite, first one, first roll.
Your player can win.
And it's just by the law, that rule, you can never have one. On that.
I was like,
I know, you're doing
I
better.
take X.
Player can win? Yeah. Okay.
Guess what?
I was wondering when you're gonna notice I'm trying to make you do the pattern. It just reversed the first one.
Determine player two's score the decision.
You didn't ring it. I see in my head and then I realized I wrote it wrong.
But you do need to know the strategies to that.
That's why I'm dying.
Have you ever seen your city around
Yeah, it's awful.
I think it's better than Ariana Grande. Like, I'd rather listen to him sing rather than her.
I love Ariana Grande.
He's working on his, like, there's so many. He's learning. He has a vocal coach that saw that and is giving him and then I saw him talk that there was somebody who actually went to school with him, and then he's like, he has a video of James, or she has a video of James Charles, the Noah twins, of what's her face. She's like, I went to school, what are these people? I know which one, and then she put a picture of James Charles. It's like, just for proof, here's my yearbook. What did he started there? I was like, fine.
That's not impossible.
I know, but people would have believed her because his picture would have been false.
That's the reason he got popular, is because he had
I never told him if I was like if I was senior year. During my senior picture, like the one that we take at school before we enter our own senior pictures.
Oh, we weren't allowed to take it.
They didn't tell us that it was senior picture day, like to get our student IDs to
They just begin starting swimming.
yeah, because like people the years before would purposely dress up
Yes.
weird, so they didn't
Yeah.
tell us. So a lot of people were in their sweatpants and sweatshirts. I just happened to dress up that day. Because someone dressed up as a nerd, like pigtails and everything. We were so mad.
I probably like go and grab one of those. Me and my was like really tall. So I did a shot. I had like feather just go. Like girl, I would cry. My hour was gone.
We all wanted to dress up like that, but then they didn't tell us.
That freaks me out so much.
I'm
like, I'll just whack it and cry. Where did you get these? You're right.
That's why it's brand new. It's I think it's an A+. Like a 97%. 97%. Unless I took it out. Probably took it out. A 91% through 89%.
No, because I just don't understand how like the 80s and 90s.
Okay, so while you're finishing that up, here's a question for you. We're going to expand on this now so that we can see how it shows us about the infinite. So I wonder if we had one lists as many rows as they want, so they don't have to stop at 6, they could keep going. Could player 1 win instead of player 2?
Yes.
Oh, who said that? Okay, so, and why do you say that's a yes?
Well, because there's only a certain amount of ways that you can do it. There's not infinite many ways.
So, because there's only a certain amount of ways that you can do it, so they can list as many as they want, so they can cover all those ways. So, so for example, they could say, okay, X, start with an X or start with an O, and then with this X, I could have an O or an X, or with if I started with O, I could have an O or an X. And then with this set of starting the first two, I could have O's or X's. Same thing here with this start. I could have O's or X's. So they could keep going like this and get all the possible ways to get O's and X's with 6 O's and X's. So that now they'd have to write this down again and put one set with O's and one set with X's. But it looks like I didn't make enough space for that. Same thing here, they'd write this down again and make one set with O's and one set with X's. So if they kept doing that, they get all the possible ways. So then player 2 goes, and it's like, well, player 2 can't miss because player 1 wrote down all the possible ways to do that. Well, let's make it a little harder. How about will player 1's winning strategy of listing all possible rows will player 1's winning strategy of listing all possible rows work if the board has infinite rows and columns? So I'd like you to think about that in your groups and convince one another if you feel like you think player 1 can win yet, or if you feel like it's impossible for player 1 to win yet. Whichever you believe, convince the other person in your group, okay? But I'll go around and clarify if you have any. Does anybody have any questions on the setup? Yes. No, yawning. Not a question, yawning. All right.
Yeah. What's the header? You broke it up. No, I thought it was just going to use some. I learned that. I wonder how big the barrel is.
It's pretty big, but there's nothing in it.
I like watching Liza Koshy's one. It's like the one where she's like, I'm a butterfly, she has her hair up, and she says the hair actually moves.
She's facing away from you, and she's moving her shoulders.
Oh yeah,
it's possible to increase the rules.
They made, there's people who made a challenge of that. As soon as you play the music, you have to throw the person with glasses and they have to put them on and do
You
the,
can always tell that Rose is the only one.
it's like Brent Rivera.
I thought she was gonna bring out, okay, they really want to. They would know that they would have a strategy, but they'd never be able to execute.
But no, but we read two, the strategy is whatever role, if player two can announce his strategy. So then you just gotta keep it up. You're right, I'm hearing a lot of good conversation. So to clarify, player two's role is infinitely long too. And player one's list is done, okay? The list is complete. Now it's infinitely long, so this is a theory, an idea, right? Player one's list is just like you have the idea of the natural numbers going on forever. Player one's list is going on forever, but it's done in that it's fixed. The list is written down. In fact, player's one list can start out like this in our list, and we'll put little dots down at the end, but they are in fact listed. These don't count. These aren't listed. Okay. So player one's list is done in that it corresponds with the natural numbers. Yeah, the player one has a list of X's and O's that goes with every natural number. There's a one-to-one correspondence between the rows in player one's list and the natural numbers. It has cardinality n. Oops, that's the wrong one. Player one's list is complete. It has cardinality n. Same cardinality as the natural numbers. So, who told us back there? You told us, what does player two do to win?
Just does the opposite.
Good. So player two can still win, doing the same strategy as you did when you won as player two. It's actually, the strategy that you use is called Cantor's diagonalization, named after George Cantor, the founder of set theory. Where you're just paying attention to the diagonal. So player two announces their number. It's going to be the opposite in the first position as the first position in row one. It's going to be opposite of the second position in row two. Opposite the third position as the third position in row three. Opposite the fourth position as the fourth position in row four. And player two's numbers going to go on forever in that fashion, and player two explains how that's going to work. So player one doesn't have that in their list because it won't. The number that player two comes up with won't match, or the X's and O's that player two comes up with won't match this one. It'll be different in the first position. It won't match this one. It'll be different in the second position. The third row will differ in the third position. The fourth row in the fourth position. That means we have just found a set that cannot be put into a one-to-one correspondence with the natural numbers. we just said, suppose there was a way, I'll just give you a minute to write that down. The set of X's and O's in rows can't be put into a one-to-one correspondence with N. Because we just said, suppose player 1 could do that. Well, player 2 found a row of X's and O's that's not on that list. No matter what player 1 comes up with as their set of rows of X's and O's, player 2 comes up with a set of X's and O's in a row that is not on that list. So we just found that there is another size infinity. There's a size infinity of the natural numbers, and there's at least one more size. And this is the size that we'll be having to spend more time looking at on Friday, because this is as far as we got in the first class. So we'll talk more about this set that's larger than the set of natural numbers. So not all infinities are the same. I'll see you on Friday.